Hello, everyone. We've got this second chapter I promised you on the fate of the universe. And at the very beginning, we're just going to start right in. What is dark matter and dark energy? I'm just going to give you definitions of it. But then after that, we'll talk about where it came from and what we see in the universe that makes us think it's there. And we'll go on to what's going to happen with the universe, what we think might happen. So, this is the thing is that if there's something out there that's matter, or there's some amount of energy out there, but we can't detect it, we call it dark. Right? The idea is there's no light coming from it. If there's no light, it's dark. So dark matter is stuff that we know it's there because when we look at things, we can see the gravitational effect, but not the light from it, which is kind of unusual. Dark energy is this other thing. It's there seems to be some sort of something that is causing the universe to accelerate its expansion. It acts essentially against gravity. It's repulsive. And we call that dark energy. We don't know what these are yet. We've got some ideas on things, but we're pretty certain something's out there, but we don't know what it is yet. What we can figure is that ordinary matter is about 4% of the universe. By ordinary, that is the stuff you can see in light. Hot stuff glowing, radiating light towards you. So stars make up a small portion of that. Most of the universe seems to be gas and dust and things like planets and small objects. And uh, so stars don't make up that much of it. But all these objects and all these accumulations of matter have some radiation coming from them. And then we figure that dark matter's about a quarter of the universe, and dark energy is the remainder. Right? Is it the universe is dominated by stuff we can't see, and of that, 3/4 is energy and 1/4 is matter. And so that's a lot of stuff we have to try to figure out what it is. And we sort of have to infer it based on what we can see, based on the gravitational interaction of things. So that's what people did. They looked at how things interact gravitationally with each other. And so when we talked about planets, we did this. We looked at the orbital period and the average distance. Right, this is Kepler's third law. But you can also look at the orbital velocity. The period and the velocity are approximately the same if everything's roughly circular. And so what we have here is a plot of the orbital velocity for the 9 planets, including Pluto, versus the semi-major axis. And we're assuming it's a roughly circular, which is a pretty good assumption. And what you get is Kepler's third law out of this. You get the uh, same sort of inverse curve like this. And that kind of makes sense. Is an object near the sun doesn't have to travel as far, it can do it faster. An object further out has to travel a long distance, it does it slower. And in a sense, what's happening is the objects nearby, you can, they're all forming from the same solar nebula. So they're going to have roughly the same angular momentum. And the stuff nearby is going fast because of conservation of angular momentum. The stuff further out is going slower. Right? So we kind of expect this. We've seen it, and we've seen it in a lot of places, and it makes sense. And this is just individual objects orbiting a star. Yeah. So rotation curves don't have to look like this. We can look at a distance from the center of some object and velocity of that point. And one of the common examples we do in physics is a merry-go-round. If you're at the center of a merry-go-round, you're not moving as fast as if you're at the very edge because the merry-go-round's fixed. And if you're not sliding around on it, you move with it, and the outer portions move faster than the inner portions because the thing is rigid. The angular velocity is constant, and that's the velocity divided by the radius. And so the further out you are, uh, the faster you end up needing to go. And so on here, if we look at things rotating like a merry-go-round and we ask what the speed that they go around versus the distance, you get a nice linear uh, plot that it actually does take more speed to go around from the outside. So, what if we plotted this for a galaxy? Well, you can make a prediction. The idea is that you start at the center. Most of the mass is outside of that center position, but as you go outwards from the center of the galaxy out, you're starting to see more and more and more mass, which means it should go up like the merry-go-round. But then once you get to the outside, most of the mass is inside your orbit, and it should decay off like the planets. Right? The outer areas should end up falling in velocity. What we actually see is that they don't. There's some growth, but it's slower growth than what's happening at the center, or it ends up being a flat curve eventually. And that's unusual. We don't know of anything that looks like this. Right? And we can model this. So what we think is that if the visible stars are the only thing with gravitational attraction, the stars should move like the picture on the left. And if there's some extra matter that we're not accounting for, they can move like the picture to the right. And hopefully you can see if you watch this animation that they are moving differently. Right? Is that the outer stars in this image on the left are moving much slower than the outer stars on the right. And that the ones on the right are they look kind of like they're going at the same speed. It's kind of hard to tell, but it's the gist is the picture on the right is one of these flat rotation curves. The picture on the left is a rotation curve like the solar system. And so if you do this for the Milky Way, here we have a plot distance from the center of the Milky Way and orbital speed, and the sun sits, you know, outside the center. And what we get is that maybe there's some oscillatory behavior, but essentially it's flat to slightly rising, slightly. And so that implies that there's some matter that we're not accounting for. Now, if you're reading the notes through the lesson plan that I sent out, literally sent it out like 20 minutes ago. So, you know, this is where you want to start reading about Vera Rubin. I gave you one article about her. Essentially, she's the one that said, that started looking at these rotation curves and noticed something was wrong. That the flat rotation curve doesn't make sense unless there's something else. So, if we look at the Milky Way and we look at the sun's orbit, what we can see counting stars, we see about 10 to the 11 solar masses. But what we can deduce from the orbital period or the orbital velocity and the distance is about 10 to the 12. There is about 10 times as much matter that we cannot see as there is actual matter we can see. And so that implies that there's some stuff around the galaxy. And so this is a model of the galaxy. You can see the luminous matter in the disk and the bulge, and the uh, the globular clusters in the halo around the galaxy. But then there's a much larger ball of dark matter of some sort. We think this is what most galaxies actually look like, is that most of them are surrounded by some dark matter. Because we can go and we can look at spiral galaxies and we can see how they blue shift towards us and away from us and deduce the orbital speeds and so figure out their rotation curves, and they are flat. They look kind of like this. They're not perfect. They do oscillate or you get minimal size as data, but essentially those are flat compared to what we expect. So it seems like all the spiral galaxies have a fair amount of dark matter. We can we can't really tell as well for elliptical galaxies. We have to use a different technique. Instead of looking at the Doppler shift, we look at the broadening of the spectral lines, which is a Doppler effect. And the wider they are, the faster the stars on the outside are moving relative to the one in the center. And looking at this broadening lets us deduce the rotation rates, and we find that elliptical galaxies have dark matter. That's kind of an unusual thing. We can look at galaxies in clusters and measure Doppler shifts as they move around the center of the cluster, and we find that there's dark matter there, and it's up to 50 times the mass in the stars. And to be clear, is once we're starting to look at faraway galaxies and clusters, we kind of have to infer the mass from the luminosity. So we figure out, you know, there's a certain population of stars that are putting out a certain luminosity, and we measure their brightness and distance. And so we can deduce the approximate masses. So it's enough to where we can get close enough in accuracy that, you know, finding out that there's 50 times the mass that we can see hidden is significant. So there's a lot of missing stuff, and you'll notice there's some weird dark, some blue galaxies in here. That will come up here in a minute in other ways of measuring the uh, the mass. Um, One thing we can do is look at clusters that are emitting lots of X-rays from hot gas. And the temperature of the gas gives us an idea of the mass of the cluster. And what they figure there is, from what we can see, it's about 85% dark matter. That seems a fair bit. And if you're at this point and you're reviewing things that were, uh, you know, you're reviewing outside work, this is where you want to look for a guy called Fritz Zwicky, Zwicky. He is a Swiss astronomer and kind of an unusual astronomer. And he comes up uh, in looking at clusters of galaxies for dark matter. And, essentially comes up with the concept as something we should be looking for in a sense. All right, so there's another way to measure the mass of a cluster, and that's to see how light bends around it. The idea is that you have a real galaxy you want to measure, in this case, the blue marks, and the light is going to pass through the cluster and around the cluster and make new images. And how much it bends is a function of the mass of the cluster. So if you can measure this gravitational lensing, it gives you an idea of the mass of the cluster. And I'll point out, just so you have a beautiful image here of what this lensing looks like in a cluster. Um, and no matter how you measure for a cluster, you get about the same sort of argument, about 50 times the mass that we can't see. So there's some questions. Does it really exist? Again, here's another pretty image for you This is a cluster with lots of gases and stuff. Um, and this is where we're starting to get to, you know, what is the dark matter? How do we figure out what it is? And we kind of have two options on this. We figure something's going on, right? One option is that this dark matter really exists. It's something that we can only see through gravity. We can't see it through light. But the other option is that something's wrong with gravity. And we don't understand it. And if we modify the theory explaining gravity, maybe we can fix what's going on. Maybe gravity doesn't work over galaxies and over clusters the same way that it does on Earth or in the solar system. But we've tested gravity so heavily through Newton's laws and through special and general relativity. We have such a good understanding of gravity around us. We have no reason to think that the laws of physics change anywhere. People think there really is dark matter. There are people who don't agree. They think that it's more reasonable that there's something a little off with gravity. And so I'll give you a link here to the idea, a counter explanation. The idea is there's basically an extra little term that you tack on to normal Newtonian gravity, the forces between massive objects. All right, the thing we did in chapter 4, F is GM1 M2 over R squared. So if you tack this on, it fixes the rotation rate that we see for galaxies. The problem that I've seen pointed out is that you need a different constant for each galaxy, is that they can explain a rotation curve, not all the rotation curves. So that's why I say it has problems. But I did give y'all a homework assignment to go and look at this and other alternate gravity theories, and you tell me what the likely answer is based on what we're talking about. We're focusing on dark matter because that's the consensus. Consensuses can be wrong, so that's why I'm giving you an open question to talk about. But the class is steered towards what you can actually see, what the evidence is. And the evidence so far looks like dark matter exists. We got to explain it somehow. So, things that we look for is fairly hard to explain without dark matter. Right? We have a cluster here, and it's basically two clusters that are moving one through the other, and we're getting X-ray emission. And it's telling us the mass of the stars in the X-ray emission. It's also telling us the mass based on gravitational lensing that we can see, which implies a different amount of mass. And so this is a measurement that's not dependent on rotation curves. And so we find it really hard to explain without saying, hey, there's something there we can't see. And so we can ask, well, what might the dark matter be? And we can think of some possible objects. One class of things is called massive compact halo objects. And what I would think of if I'm hearing that is things like brown dwarfs that have cooled off. And you remember brown dwarfs from the formation of stars, or white dwarfs that have cooled off. You think of the remnants of red giants that have, the leftover cores do cool off eventually. And so these remnants might be there. There might be significant hot objects, but not hot enough that we can actually detect them. Right? They may be very cool compared to the other objects we can see. And perhaps there's other forms of it. Um, but there's another class of objects that are essentially particles that we can't see because they don't interact with other particles. The interaction is usually where we get some light produced, and we don't see interaction between these particles, so we don't see any light. And the gist of it is we don't know exactly. Um, we're going to focus on small particles, right? But really, the matter just needs to be not as bright as a star because stars are what we're trying to see, stars and gas and dust. So it needs to be something cooler and dimmer. And it's possible it's just extra matter that we can't detect. But the class that we focus on is these weakly interacting massive particles. So things like a neutrino, but more massive and weakly interacting. They don't deal with other stuff. We don't have a great understanding of what these are. We haven't detected them because, by definition, they're hard to detect. But people are looking for them. And it seems like the likely thing because we're pretty good at seeing ordinary matter. Um, and the gist of it is looking at the abundances of produced uh, light elements kind of leads you to believe that we can't figure out how ordinary matter can make up the matter we're not seeing. Is that there's got to be something else we don't know about. And so that's our argument. There's not enough ordinary matter, and these things that we're looking for could just be leftovers that don't interact with anything. Um, and we think that this could help explain how galaxies form. We think this could help explain what we're seeing. Interestingly enough, you've noticed now I've mentioned WIMPs and I've also mentioned machos, the massive compact halo objects. Astronomers don't make good jokes, just so you know. So we think that galaxy formation is dependent on dark matter. What's here is if we look at a patch of the sky, we can label out where stuff is moving toward and at what speed. And that's kind of what we want to know about. How is these clouds of matter causing contractions? And we think that dark matter provides extra gravity in a sense. They don't interact with anything else, but dark matter provides extra mass, which helps traction. And because the because the WIMPs cannot radiate away, right? Normal matter radiates away its potential energy as heat and light, but these WIMPs can't until it leaves a cloud of them around the galaxy as it forms. It helps start the collapse, but then the normal matter is the stuff that can fall further and further in as it radiates away. And so what we're seeing in large scale on the universe is dark matter keeps pulling stuff to high density areas. Is all right. So everything's expanding away from everything else. But if you look at a cluster, the cluster tends to stay together. There's regions that get denser and denser instead of spreading out. You have to look even higher scale to see that it's spreading out. But after taking away Hubble's law effects, the universe is getting more and more lumpy. This stuff is flowing towards the denser areas. And so that means that there's structure on the universe as a whole. And when we map out what we can see long out through the universe, what we see is that there's lots of clusters and superclusters, big structures with voids in between. Filament. You can see fair structures that spread out through the universe. and in large areas that don't have anything in them. And so when we model what goes on with the universe as it forms, dense regions draw in more stuff. There's more gravity pulling stuff in, and the dark matter is helping to do that. The universe gets lumpier over time. And we can model it further and see how the universe goes from a soup of stuff into lumpy strings and filaments of groups and clusters of galaxies. And this sort of structure looks fairly similar to the structure we see in the background radiation. So, this leads us to the fate of the universe. And dark matter and dark energy is going to have to play a role in what's going on. We haven't talked much about dark energy either. There's four possibilities as to what can happen to the universe. All right, so there's the Big Bang, and the universe expands outwards. If there's enough matter in the universe, gravity wins. Gravity wins, and the universe contracts back to a point. If there's just barely the right amount of matter, the expansion is going to slow more and more and more. It's going to approach a fixed size. There's some size of the universe that's the maximum of value, and it's going to approach that, but it'll continually expand. Um, there's a chance there's not enough, and the expansion will occur linearly forever. And then there's what if there's dark energy? What if there's something pushing stuff away faster than gravity can pull it back? That is the accelerating expansion. That's our four options. Only one of them leads to a recollapse. Everything else leads to everything gets further and further apart. And it critically depends on how much dark matter there is, because we can count all the stuff we can see. And essentially, the stuff we can see leads us to think that it's a coasting universe, that there's just not enough stuff. But with dark matter, you can get closer and closer to a recollapsing universe. So which of these that happens depends on how much dark matter there is. And currently, there's not enough. We think that the universe is going to expand forever based on that. But when we look at the expansion of the universe over time, it's speeding up. We think that there's some dark energy, there's some other thing pushing the universe outwards. And how much of all of this stuff there is depends on our estimates for the age and the amount of matter in the universe. But in particular, when we look at white dwarf supernovas, we're using these as standard candles to figure out the distances to objects. But the light has to travel to us, and while it's traveling to us, the universe is expanding. So the sources are not where we saw them uh, when they emitted. The sources are not where we're seeing them; they're further away in a sense. So the brightness of these white dwarf supernova is giving us an idea of how much the expansion has occurred since they exploded, and they occur at different distances, which means they occur at different times. But we're certain that the physics behind them is all the same, so they should have the same luminosity. And so it gives us an idea of how much the universe expands. And so on this graph of this is magnitude and redshift. So the redshift is a measure of the distance, and the magnitude's a measure of the luminosity. And this light dotted line is what we think things should be. And then you can see the data points as we go further and further out, they're getting fainter and fainter and fainter, which means these stars are further away than we think they should be. The expansion is getting faster and faster. Now, we're trying to deduce that from the we're trying to deduce future behavior from past data, but we can model what the collapse or what the expansion should look like based on how much matter there is. And all these data points are fitting on the model that says the universe expands. Right? And here's another graph of fitting these supernovas to a different curve that says that the expansion is going to speed up. So there's more evidence for this dark energy is the shape of the universe. The universe is flat. And we can look at the background radiation and tell that the universe is flat because it's basically in the same. There's no structure, no real structure to it. It's pretty similar everywhere. So what we can see doesn't allow for a flat background. We have to fill in with extra energy to curve the universe back to flat. So this leads us to the fate of the universe. The universe is probably accelerating. Let me talk about the collapsing universe. That's kind of more of a story. If if the universe were to recollapse in about 10 billion years, the universe, right, in a couple of billion years, we would start to see the Hubble redshift turn into a blue shift. We'd start to see stuff approaching us from all directions as the universe is contracting. And in about 10 billion years, what we would see is the remnants of everything starting to collide together. You'd see more collisions in galaxies, you'd see more collisions between stars, you see things falling closer and closer together, you'd see more black holes forming, more eventually everything falls together into one point, and that would be the collapse. If it's some sort of expansion, though, what we figure will happen is as as material expands out through the universe, it's getting further and further away. What we'll see is less and less galaxies in the sky. Stuff will get further and further away, and stars will die. The galaxies will recycle the material, but eventually, they'll they'll evolve to old and red stars, and those will die. They'll run out of energy, and eventually, we'll have cold remnants. Um, the uh, energy will be lost through radiation, and material will fall into black holes, and eventually, everything will form black holes. And then those black holes will radiate away energy, and eventually, the eventual outcome is radiation everywhere again. A very low temperature, low energy radiation. Now, there's some other explanations as to what could happen. If you go research the fate of the universe, and maybe you should look at it. Um, there's some ideas as to what happens when um, when you're trying to describe the behavior of particles over huge amounts of time, and what happens when you're trying to describe the evaporation of black holes and that sort of stuff. So what we figure will happen is this constant expansion, and basically everything kind of fades away into radiation at some point. that concludes the chapter. So, what's next is the last chapter in the text, chapter 24. There's a preview. We're probably going to do that, which is life. Is there stuff out there? And would we ever talk to it? And then, if there's sufficient time, we'll probably do something about manned spacecraft. And that's something we've generally not hit. And we'll talk about that for a bit. We may hit some other topics. If there's something you want to talk about or you want to hear about, it would be a good time to email me. Let me know what you want to know. And I've got a couple of weeks to work on it. But yeah, the end of the semester, the end of the year is closer than you think. And that implies that assessments and finishing out your grades is closer than you think. So keep up the good work. How do I close this now? I've done this like 1,000 times. I don't know how to close these.